All right, so we're picking up on 4-3, multiplying matrices. All right, so is matrix multiplication commutative? We talked about this a little bit in class already. I don't remember with which example, but, well, I do actually, now that I think about it. Okay, when we talked about multiplying a matrix, so if we have matrix A, my pen's not going to work. If we have matrix A, which is a 2 by 3, yeah, awesome. Let's see if I can try again. There we go. Okay, if we have matrix A, which is a 2 by 3, and matrix B, which is, yeah, let's say a 3 by 2. Can we multiply A times B? Yes, right? Because, right, because it's a 2 by 3 and a 3 by 2, and these middle numbers have to match. Perfect. Can we multiply B times A, though? No, because B is, oh, okay. B is a 3 by 2, and A is a 2 by 3. Okay, so this one we can do both of those. All right. But if we do a, okay, so if we had like C, which is a 2 by 3, and D, which is a 3 by 5. Okay, can we multiply C times D? Yes. Can we multiply D times C? No. So is the matrix multiplication commutative? No. Okay, so let's explain the C and D. So C and D would be, or CD would be a 2 by 3 times a 3 by 5, and they would have the same middle number. So yes, we can multiply them. D, though, is that 3 by 5, and C is a 2 by 3. Here is where our problem is. We cannot multiply 5 if we have a 5 and a 2 in the middle. So yeah, we cannot multiply in any order, and that's a very basic understanding of why we cannot. Okay. All right, awesome. The other thing is if you get further in, even because of the way that we multiply the numbers, we also like how we multiply the row times the column, and then we sum them. It also will lead to a different answer, even if they will multiply to each other. So that's kind of crazy. So even when we do them, like when we line them up and multiply, let's see. So if we would go back here to these, if we change the order, right, if we flip these, they would lead to different answers when we add them.
So even if you can like do AB and then flip it to BA, you wouldn't even get the same answer?
Not necessarily. Correct. Because we're multiplying the row and the column, and so then the rows and the columns have switched places. So they are the same numbers, but they've switched. If we have some time later, maybe we'll look at a couple and see, because you're right. All right, so is matrix multiplication commutative? The short answer is no. It is not. However, every matrix has an additive identity. Remember, the additive identity is 0. Okay, when we get it. So only square matrices have a multiplicative identity. So like when the additive identity is we add 0. So remember those were those 0 matrices in like the beginning? It was like a matrix full of zeros. Okay, but only a square matrix has a multiplicative identity. Okay, and that's, yep, so a square matrix, you got it, is a 3 by 3, a 2 by 2, a 4 by 4, 6 by 6.
So it's just the same number?
Yes, it has to be a square.
So it doesn't matter what number it is as long as it's the same number?
Same number of rows and same number of columns. So this one here is a 3 row by 3 column. So it's a square matrix, a 3 by 3. I saw, oh, it got put over here. Good question. Go ahead, Brandon. What was your so?
So what are you saying that you can't do with them?
No, so you would see, so if we have matrix A times the identity matrix of A, or times A, is going to equal A.
The identity matrix
Is I.
which means what?
I stands for identity. So when we multiply by this matrix, the matrix that we have is going to stay the same. So just like when we added before, okay, then the matrix is going to stay the same. And we will use it later for solving matrices. Right now we're just introducing it.
The identity matrix is
Um,
that's what we multiply both things.
we're just gonna practice multiplying by an identity matrix first. So here's the thing though, the key on that, the elements on the main or the major diagonal, okay, so that is this one, okay, are 1. All the other elements are 0 in an identity matrix. So if we have a 2 by 2, it's going to be 1, 1, and then the rest are zeros. If it was a 4 by 4, then it would be 1, 1, 1, 1, and everything else would be zeros. So it's just that one diagonal that's full of 1s to be an identity matrix.
So that's every identity matrix, no matter what.
Yep, because they're only square, and the diagonal is all 1s, everything else are zeros. Okay, so the reason we have a so then the definition, the actual definition of a multiplicative identity matrix, it's a square matrix with 1 as each element on the main diagonal and 0 as every other element. That's your definition, which we just defined. But let's actually then look at the example and how we're going to use it. Okay, I was like, it's not going to. So example 4, it says, given matrix A, find IA and AI. We do need an AI to find that. All right, so first of all, I identified my I. Okay, so it's just.
Quick question.
Yep.
Can you only have an identity matrix of a square matrices, or is there?
Yes.
Okay.
You can only have an identity matrix of a square.
Okay.
You got it. No circles either. Okay, so then I am doing I times A. So my I is the first one. And remember, I blocked it off because like last week, if you remember, I had them kind of set up so we could think about like filling in this spot. You don't have to do that. It was just me trying to help it like facilitate making it easier for you. Okay, so this first one is 1 times 3 plus 0 times 8. So 1 times 3 is 3. 0 times 8 is 0, so this is just 3. And then if we move down to the next, over to the next one, 1 times negative 1 is, we put there, and then 0 times 12.
I need to break this out of it, or I'm not going to follow.
Okay. And then 1 times negative 1 is 1, plus 0 times 12 is 0. Sorry, so negative.
So we're doing I by A right now, right?
I times A. Uh-huh.
Okay, so the I is going to come first, and then it's not changing anything. Okay.
All right, so then the next one, we're going to have 0 times 3 plus 1 times 8, which is 8. And then for our last one, the spot over here, we're going to have 0 times negative 1 and 1 times 12, which is 12.
It didn't change it at all.
Didn't change it at all, right? It's the exact same.
Not supposed to?
It was not supposed to.
So may I ask what the point is?
Because at some point, we will use the identity matrix to actually solve for unknown, like to solve a variable.
So
Like we'll have to get one into an identity matrix.
Be a variable inside the matrices, and we use that to.
Yes. Yes. All right, so it didn't change anything at all, but it's not supposed to because we're multiplying by 1. Yes.
Can I ask a question that might be ahead of what we're doing?
Sure.
So when you're finding the variable and you set it equal to the identity matrix, since everything else is either 0 or 1, when you do that, is it just going to tell you what that variable is? Because that variable will become a number and everything else be a 0.
Yes.
That's easy. Or sounds theoretically easy.
I like it. I like it. Yes. All right, so let's do the next one where we're doing A times I. So this time, because my marker's working so well, there we go. So our A is the 3, -1, 8, 12. Our I is not 0. I have 0 on my mind. Do what? Yeah, it's still recording. It's 1, 0, 0, 1.
Had the trash talk Ethan or something?
No. The time disappears.
Yeah, when it gets to 10 minutes, the time disappears.
Okay.
You're good. All right, so let's do this first one. So we're going to have 3 times 1 plus -1 times 0. Okay? And let's do our next one then. So we're going to have 3 times 0.
It's gonna be 3 times 1 plus
-1 times 0.
-1. Yeah.
Okay.
Yeah.
Times 1.
Times 1. Okay. All right, perfect. Then let's do the next one. So 8 times 1 plus 12 times 0. And for the next one, it's going to be
0
plus 12 times 1. All right, perfect. Okay, so what's 3 times 1? 3 minus 1 times 0, or plus -1 times 0 is just, or here, maybe this is what I should do. Let me come back up here. So this is 3 plus 0, right? So it's going to be 3. 3 times 0 is 0, plus -1 times 1 is -1, so this is just going to be -1. 8 times 1 is 8, plus 12 times 0 is 0, so that's 8. 8 times 0 is 0, plus 12 times 1 is 12. What happened? Nothing. It didn't change anything because we're just multiplying it by that identity matrix. We're just practicing at this point, essentially. All right. How you feeling about this, Brandon? Other than the fact that like we just wasted 2 minutes of your life.
Yeah.
Okay.
I'm gonna call my lawyers.
Please don't. I don't think you have a case. All right. So matrix multiplication allows a system of equations to be written as a matrix equation. So this is at 13 and 15 that we didn't, on the homework that we didn't do. Okay, so what you do is each variable aligns. Like here's your x, your y, and your z, essentially. So we pick the coefficient that came in front of each one. So a 3, there was no number in front of the y, so it's a 1. So what's in front of the z? -4. We always take that sign with it. So this becomes -4.
So that you're just taking a 3-digit system.
Yep. Uh-huh. Since there's 3 variables, there's 3 columns.
Do you have a protractor I can use?
Mm-hmm.
Can you put any equation into a matrix system?
Yes, you can.
Any system?
Mm-hmm. Oh, sorry.
and
Uh-huh.
Sorry.
You're good.
Then what happens?
Thank you.
Okay, I was like, we'll get there. So for the next one, we have 2, 3, and what goes in our z column? 4. And for the last one, we have 1, -1, and 2. All right. So then we have a column that we name x, y, z. Okay, so it's like we take this one, right, and we bring it into a column form. That's kind of one way you can think about it. And then this is called our constant matrix. And what is it from? That's the answers, right? The answers to it. So we have a coefficient matrix, which is A, and a constant matrix, C. So a matrix equation here would look like this. A times X, that's our variables, equals C. A capital X.
Oh, so that whole thing is
This whole thing,
X.
would be matrix X. Good to know, right? It's important stuff. Kind of. It is for our unit anyway. All right, so example 5, write the system as a matrix equation. What do you notice that I did?
The y is on the left side, and then it equals y.
The y is on the left side and it equals y. So what form is this in?
That's y.
This is slope-intercept, but they were not in slope-intercept. What do they need to be in?
They need to be in standard form.
Standard form. Okay, so we can't take them. We don't want them in this form. We want them in standard form.
Why?
Well, they all have to be, we want our x, our y, and our z, and then the answer. So we can put them in the matrix form. If they're in jumbled forms, like this one, right? We have the y over here.
But that's not in standard form.
Right. So I put it in standard form. Touche. Technically, in a standard form, you can't. So this is more standard form. Like, so we don't have to call it, like, you're right, in standard form, that is not supposed to have a negative. So we can just say that it's in ax plus by plus cz form, if that is easier for you. Because you're right, in standard form, we're not supposed to have the negative. In this case, we don't care because we're not solving it. We just need it to be in.
So you just need it to have x, y, and z.
Yeah, we just need it to have x, y, and z.
So how do you change it?
Well, just like you balance any equation, right? So we would subtract 2x. So we'd have negative 2x plus y equals 5. And then we need the z in there, so I added the 0z so we could see that. And we could put all of our numbers in there. So let's try it for b. Okay? So in this one, we only have a y and an x and a x and a y. There is no z, so it's a little simpler. But do you see how they're all jumbled? Okay, so we want to get them into an order that's the xy order. So we're just going to change these around, and we can write, well, this is negative 8x plus 3y equals 11.
And then the other one, you can add 9.
Okay, this one we're going to have to add 9y.
Yeah, and subtract 45.
Because remember, okay, because we've got to get everything, like my equal sign is like my divider. So I'm going to have 2x plus 9y plus 45 equals 0. But I need this 45 over there, so I'm going to subtract 45. So then I have 2x plus 9y equals negative 45. So this one becomes 2x plus 9y equals negative 45. We good with that so far? Okay. Changing them over to quote-unquote standard form, yes. Okay, so now we had to do all that work just so we could put it in matrix form. So, Brandon, give me the matrix form, the first row.
8, 3.
Not 8. Negative 8, 3. Okay, Josh, give me the next one. 2, 9. What's going to go in here, Brandon? You got it. Equals, Josh, what goes in here? 11 and negative 45.
So that's them added together or multiplied together?
Multiplied.
So just negative 8 and 3.
Doesn't have to be. Because you're right, negative 8 and 3 does not have to equal 11.
Oh, I see where you're
We're just,
now.
okay.
I see now.
Okay, gotcha. Yeah, I was like, those numbers are coming from the solutions.
What is the x and the y for?
Because if we actually did the matrix out, we would be able to get back the equation that we have.
Okay, so you can.
Because we would do.
We're not solving it all. We're just changing forms, basically.
Yeah, we're just changing the form at this point. And so.
This is teaching us to take equations and put it into matrices.
Yes.
And then I'm assuming later on we'll be using matrices to put them into equations and then solve them.
Yes. But like this one, we're actually going to use this concept to write the equation and then to solve the system. So example 6 says the following is a predator-prey system for F sub O and R sub O. Are the number of foxes and rabbits in the current year. And F1 and R1 are the number in the next year. So we've got this awesome equation. It says write the system as a matrix equation and use it to predict the fox and rabbit populations next year, if there are currently 50 foxes and 2,000 rabbits.
So is this solved?
We're on the verge of it. Okay, so first of all, where did this all come from?
The equation.
The equations, right? So we took the equations and put them into the matrix equation.
It gave us those equations, right? You didn't pull that out anywhere?
Nope, they gave us those equations.
Okay.
Yep, I didn't pull that out from anywhere. That's the information they gave us. So I pulled that though and wrote our matrix, wrote it as a system, as a matrix equation. Okay. Now it said use it to predict if we know we have 50 foxes. That's our initial F sub O, right? Is the number of foxes in the current year and rabbits. Okay. And our R sub O is 2,000. So I plug those in for that place, which is how I got. Yep, so the foxes was 50 and the rabbits was 2,000.
And you just plugged that.
So I just plug those in. So when I get an answer out, my answer is going to be the foxes for year 1 and rabbits for year 1. Okay, so let's actually solve the system. We're going to have 0.8 times what?
FO?
Nope, we're solving the system. 0.8 times
There? Oh, okay.
50.
50. Okay, I
50.
was thinking of the first thing.
Okay, plus 0.02
Times 2,000.
times 2,000. Man, I left myself a lot of room and I still can't fit it in there. Are you with me?
Yes.
All right. So then for the next one, we're going to have negative 0.2 times 50 plus 1.2 times 2,000. So we might need a calculator. Brandon, do you have a calculator?
I do have a calculator.
You have one? Okay, perfect.
You sounded so confident when you said that.
All right.
I do have a calculator.
I do. It's a mine.
It's a mine.
So 0.8 times 50 I got is 40 plus.
I'll do the bottom one to join it then, actually.
I was like, I'll take confirmation. Like, did you get 40 for 0.2 times 2,000? Again?
What? Times 2,000? We're not doing 2,000.
Yeah. 0. Point.
Times 50? I thought that's what we were doing.
We did that one. I got 40, and I did this one, and I got 42. That's what I'm asking. Did you guys get?
40 or you got 42?
I know that.
I got 40 also.
I got 10 for
Ha ha.
the bottom left. I got
You got 10 for the bottom left.
Struggles of a mathematician.
Okay.
The grammar guy.
Not me.
That one says 40, and let me check the other one. 0.02
No.
times 2,000.
I'm so tired.
Yep, 40.
Okay. So then I got 2,400 here.
Okay, let me do that. 1.2 times what? 2,000?
Mm-hmm.
2,400. Yep.
Okay. So 40 plus 40 is
80.
80. And 10 plus 2,400 is
Is 2,410.
2,410.
That's how
And
foxes and rabbits we are.
hold on, that's. Oh, time out. This was a negative 10.
No! Shut
I was.
the door.
Well, cause see, I had the answer over here, and I was like,
Okay, 2,390.
I was like, that's not right. Okay. So 2,390. Okay, so how many foxes will there be next year?
80.
80 foxes.
There's gonna be a gosh dang lot of amount of rabbits.
And how many rabbits?
2,390.
2,390 rabbits.
You don't realize how fast the freaking rabbits.
Yeah, their growth is exponential. Like their reproduction rate for rabbits is exponential.
It's like almost as fast as a rat, and rats are crazy.
Yeah. So, do you see now how we can like take the system and like solve it pretty quickly?
Yes.
Like when we have this word problem situation. It's kind of awesome. All right, so then for your homework, I want you to do 13 and 15 because we didn't do those. Okay, well, if you did do them, great. If you did not understand them, then you can go back and do them. So 13, 15, and then 19 through,
13, 14, 15, or just 13?
13, 15, 19.
yeah, 13, 15, if you didn't do them. 19 through 29, odd.
19 through 29 odd.
And then 35, A and B. So we're just finishing up the rest of the homework that we didn't get a chance to do because you were supposed to do 1 through 17. But I didn't see 13 and 15 in there. So we're doing the rest of that assignment. Okay.